We start now a new sort of chapter of the class, and we're going to talk about application security. So how to look at the security of applications. We have seen protocols, and now we're going to look at application, which are actually the code that runs and provides services, either locally, like a word processing tool or an editor, or remotely, like a server. And of course, the behavior of an application is not only the code, but is also determined by the execution environment. That means how it is installed, with the what depends on the environment in which it is executed. When I talk about the environment, I talk about all those variables that are created in the memory of a process to reflect certain parameters of the host. And of course, the basic idea is that you attack applications so that you violate their security. The security of the application itself, as we'll see, or the security of the environment as a whole. And of course, we talk about integrity, confidentiality, and availability as our general categories. If you look at our threat or application model, we have an application, which is the code and the memory that actually runs in a process. We have the environment around the application. The application might interact with a local process on the same operating system, could interact with entities on the network, they're remote, and of course interact with the file system, and maybe through a terminal with an interacting user. And as you can see, whenever you have an interaction, you also have a way to influence the behavior of an application. So you can imagine attacks fundamentally coming from all these possible sources. So application vulnerability analysis is the process to look at an application in a particular context and understand if there are vulnerabilities. Design vulnerabilities, implementation vulnerabilities, or deployment vulnerabilities. Okay, we're probably most of the time familiar with the second, but not so much with the first and third. So design vulnerabilities are interesting because these are vulnerabilities that are intrinsic in the logic of an application. So the application has been designed in the wrong way. There is nothing in the code that is really a bug. It's the design that is unsound. Who has an example of a design vulnerability? Yes?
Maybe the Equifax system where their web server could directly access their entire database, not just the parts it needed to.
For example, that is a design. I guess it's a design vulnerability. That sounds. I don't know the details. That sounds more like a deployment vulnerability. Maybe they could have deployed things differently. What is another problem with the yes? The R protocol, for example. That's a very good example. All the remote shell, and as a design, having people being authorized to run commands when they come from a specific IP address, that's not a good idea. It's not a good design. Regardless of the perfect implementation, there are so many cases in which this can be abused, in which can cause problem. That's why we don't use it anymore. Okay? So the problem with these vulnerabilities is that they're incredibly difficult to detect automatically. So while a lot of research has been done in automating buffer overflow, format string vulnerability, the identification and the exploitation of these vulnerabilities, these kind of vulnerabilities are super difficult to automate. Because how do you teach a machine to look at an application, find it what it does, and find the problem with it? Just finding what it does is, violating the halting problem. Because if you can find what it does, you mean that you can, in the general case, determine if that application terminates, for example, which, as we all know, is algorithmically impossible in the general case. Another interesting thing is the confused deputy problem. Sometimes a design brings the application to do something that is supposed to do, but in a way that causes security violation in the system as a whole. For example, a classic thing that malware does to download files on a machine, they don't open a connection back to somewhere and download the file. They actually connect to Internet Explorer and say, hey, can you please download this file on my behalf? Why? Because there are controls in the operating system that say, oh yeah, Internet Explorer, the browser, can go out on the internet and download stuff. But this process just started, So in a way, this malicious process deputized the browser in order to download a file. So there are many situations in which you, as we will see, you will use something to, in a way, create sort of an unusual condition that will trick an application into doing something that it shouldn't do. Okay? That's called the confused deputy problem. A good example is the FTP-bound scanning that we saw when we were talking about FTP. In a way, you're deputizing the FTP server to do the scanning on your behalf. You have a deputy that does something for you, is playing the protocol. You're not breaking the security of anything, but you're just, sort of exploiting his availability and his desire to play around the rules in order to do something like bypassing a firewall or something like that. And of course, there are vulnerabilities that are implementation vulnerabilities, and this is the bulk of the stuff that we will see, because they're easy to describe, they're easy to define, and in a way, they're also easy to automate, at least in the vast majority of them. You can always find algorithms that will attempt to find instances of these vulnerabilities, and these, of course, usually are caused by the fact that there are unexpected, unhandled, or mishandled conditions that the application is performing. So cannot deal with certain input, cannot deal with certain exceptions or errors, cannot sometimes deal with the interleaving of certain events, or it is not able to produce output that is correctly sanitized. And then, of course, there are deployment vulnerabilities. And in this case, the problem is the application has been installed, configured in a way that is unsafe. What is an example of a classic deployment vulnerability?
Having access to, in your config files, to the slash from the web server.
For example, very good. What else? Yes?
Running like web server as root.
Running a web server as root, that's a classic misconfiguration, very good. Another example is having default password, like leaving a bunch of IP camera with the default service account, username and password, that created the Mirai botnet and one of the most massive denial of service attack in history. That's fundamentally a deployment problem. It's not that we cannot do username and passwords, is that if you leave a bunch of machines deployed with a default username and password, people will take advantage of it. Okay? So the idea is that these problems can be easily solved by deploying the same application unchanged in a more secure way. Yes?
I think you mentioned Cloudflare last time. How does that work?
But that's a different thing. Cloudflare is a protection against DDoS, and we're not going to go there right now. But if you're interested in that, I'll talk to you about it. It's fundamentally a content distribution network that prevents routes traffic so no one side gets overwhelmed. But it is not in the scope of what we're doing right now. All right? So the other, apart from vulnerabilities in design, implementation, and deployment, another important way to look at attacks and vulnerabilities is remote versus local. So in a local attack, what you have is presence on a host. And what you're trying to do is actually achieve an increase in privilege. So you already are a user, imagine a user on a Unix system, and you want to do more. You're already an application on an Android phone, and you want to do more. Do more could be do something that another application does. So you move with the same level of privilege, but in another context. So you can act as another user, for example, or another app, which in Android is fundamentally the same thing. Or you want to escalate your privilege and become root administrator or something that has more access to the system. In general, these attacks are easier to perform because you're already on the system and there are a bunch of variables that you know about the system. You see what the operating system is. If there's certain configuration that are blocking or not blocking your attacks, you can actually find out about them. So they're usually easier. But of course, you need to have local access. And then there are remote attacks. These are the most difficult to carry out, but they are also more potent, or they provide more capability because they give you access to a system that you never had access before. So you can remotely execute code, or you can remotely modify the configuration of something. And of course, oftentimes you don't know exactly what the parameters of the remote systems are, and so you cannot figure out what's going on. For example, if you remember in that attack against how PHP chooses the session, one of the parameters was like, if I can run on the same system, I can extract a number of information that would allow me to reduce the available entropy in generating that particular cookie. So we will look at the lifetime of an application, which of course is the writing code, usually in a high-level language. Then we have translation, we have either interpretation or compilation. Then we have loading in memory, execution, and then the application terminates. This is how applications are written. Of course, they're written once and executed many times, so you're very familiar with this concept. Let's talk briefly about interpretation, because it's something that we will see last. There is one aspect that is important in interpretation, is that most interpreted languages have a way to execute code dynamically. So they can take a string, call eval, and suddenly your string becomes code that gets executed immediately. This is an important aspect because that means that your static analysis just went out of the window, meaning that you cannot really be sure of what code will get executed at a certain point, especially if the application goes from the internet, downloads something, and executes it. So, and that's why, for example, a lot of obfuscation involves exactly this. You will see, obfuscated JavaScript. Oftentimes, it's just one big string encoded, or sometimes even encrypted with different levels of potency, quote unquote. But eventually, when the JavaScript gets in your browser, it gets decoded and executed. And that's a way to prevent, for example, the ability to analyze the code statically, because, of course, static analysis can be faster, at least in certain cases, or to generate signatures, which is a form of static analysis, if you think about it. Okay? In general, when something is interpreted, you can look at it as the actual source code, but in most cases, it's some kind of bytecode. For example, in the case of Python and other languages, it's translated in an intermediate form, and then each instruction is fetched and executed one after another. What we will deal mostly is compilation, mostly because it's the analyzing source code or interpreted code is in general easier. You know clearly what's going on. One of the most difficult things is analyzing binary code. And so we will look more at binary code, and from now on we will look at a lot of details of assembly, binary instructions, and so forth. Keep in mind, there is a preprocessor that makes sure that all the code is there through includes and things like that, macros, and then the compiler will transfer it into assembly. So if you take a program and you patch the -s, you will actually see the assembly of the program. The assembly being the high level, not binary. If you compile and linked, of course, you will get to an object code. You do this through the assembler, who take the assembly and generate a binary object. Okay, so you go from the C as you know it. After the preprocessor, you take all the macro and include. You have only C, and then you have the actual first stage of the compiler, which produces assembly, and then there is the assembler that actually create a binary object that can have, for example, relocation information that tells you, if you load, you load this in memory, you have to adjust all these things because, of course, the code that is in a file is not exactly what happens to be loaded into memory. And we will see that this can also have information about symbols and debugging information. Oftentimes, for example, if a binary is stripped, all this information has been removed, which makes it harder. I would say that the worst case scenario is one in which the binary has been statically linked. That means that all the code, even the code for printf, from libc, all those additional function has been put in, and then it is compiled, and then it's stripped. It's difficult because when you're analyzing this binary and you get to printf, you don't know it's printf. It's like this very weird function that gets a variable number of arguments, and then you get, after 3 hours that you are in the process, like, oh, this is printf, And as we will see, there are tools that actually try to solve this problem using function signatures and things like that, but it is a problem. Yes?
What tools are available to strip it?
Oh, to strip it? Mm-hmm. To strip the binary, I think now I think you can use NM as a tool, or even just with GCC you can generate a stripped binary. So, but that's just an option on the compiler. It's just do not include the symbol, and also an option statically linked everything. I don't think there going to be any stripped binary in your homework 3. Of course, once you have all the object created by the assembler, there is a linker problem. So all these might reference each other, and so there is the step in which the binary object is compiled with libraries or reference to libraries are created, and fundamentally this creates a binary that is ready to be loaded and executed. Okay, and of course some parts can be dynamically linked. That means that will be resolved, the symbol will be resolved at load time when you actually execute the program. And one reason for having runtime linking is because you can have libraries that are shared among different programs. So in memory, you have one version of libc, something that everybody uses, instead of including the same function all over again in every binary. Of course, the advantage of having something statically linked and completely combined is that you can execute it and it doesn't have any external dependencies. So if a library is misconfigured or is not present into a system, it will not fail. All the code that needs to be executed is there. The two most common executable formats are ELF and PE. ELF is used in Linux, of course, but it can be used also by others, and PE is the executable formats for Windows. Let's talk a little bit about the ELF file format. It's relevant because actually, as we will see, how this binary file is loaded in memory and executed is relevant from a security point of view. It tells you, for example, which parts of the binary you can modify, which you cannot modify, which ones you can read, which ones you can write, and so forth. So from this point of view, this is an important set of information. ELF is called the executable, and linkable format is architecture independent. It means that you can actually have ELF for x86, ELF for ARM, ELF for Spark, MIPS, whatever you want. You have 3 files of types, what we call relocatable. So that means that they need some relocation before they can actually be executed. Executable, so means that all symbols have been resolved. They can be just loaded in memory and executed. Shared, this is the format used by shared libraries. So they provide fundamentally services to other binaries in terms of code. And core dumps. So these are actual, core dumps, snapshot of a program memory image that are generated usually when there is some kind of fault. Tools, super useful, readelf file or object dump. All these tools are available in Linux, and you can use it to see what information is included. And they're command lines, so you can script and generate all sorts of different information. The ELF file format is relatively simple. There is a header file that contains, for example, the architectural for which it has compiled, the entry point, so where you jump in when you start the program. And then fundamentally, you have two headers, the program header table and the section header table. The program, is the program header contains a list of segments, which is how the loader fundamentally sees the file as to be loaded in memory. So this chunk goes here, this chunk goes here, and then the section header table defines section which within a certain segment, and each of these sections has, for example, specific rights or specific characteristics that tells you what's in a certain section and what are the access. And in fact, each section has a header that specifies the permission and the type. For example, a section called progbits means that this is part of the actual application, code or data. No bits is part of the program that doesn't need space in the file. So such for example, data. They say, oh, I want this array needs 64K of space, but it's uninitialized, so there is no reason to have the 64K in the actual file in the file system, but it will be created as such in memory. Symtab and DINSym, symbol tables. You have string tables. You have relocation information. All this stuff is can be a different type of section. And also you have flags for each section. For example, you can have, the section is actually located in memory. You can have something that is writable, something that is executable, and so forth. These are examples of typical sections. The .text section, the name, it's usually the program code. So of course it's type progbits and will be allocated in memory and will be executable. Then you have, for example, initialized data and uninitialized data. You have read-only data, and you have pre and post code execution routines. Okay. This is the basic idea about the ELF format. The PE format is different. We will not go in details because it will make this way too boring. But the basic idea is that initially there was a COM program format that allowed only program up to 64K. And at the time, of course, everybody thought that would be always enough for the rest of history. That was not the case. The COM format is super easy. You just take the binary, you load it in memory, you jump to it, and that's it. No relocation, nothing. Of course, then there is the EXE format that allows instead to load the program in different parts, but this requires reallocation and therefore relocation, and therefore it is a little more complex. And this is all we will see about the PE format, and instead we're going to start talking about the beloved x86 CPU family. Started as 886, 16-bit registers, so very small. They were in real mode. The way they dealt with referencing more than 16 bits of data was fundamentally to use this register. They would just sort of shift the register, use the 4 bits as the initial address and the 16 bits as an offset, so they could actually reference 2 to the 20 memory addresses. The 286 introduced protected mode. In this case, they introduced the concept of a segment that instead of being just an extension of the address, the segment register would point to a segment table that would actually have information, for example, about the protection of that particular segment, where it starts, where it ends, and therefore you could even, for example, say, hey, you are accessing an offset that is outside that segment. And of course, this introduces some indirection, but allows for a lot of flexibility. Then finally, in the 386, we have 32-bit register, 32-bit protected mode, so we have a lot more memory that can be addressed up to 4 gigabyte. Then there are, from the 486 on, there were a lot of extensions like multimedia extensions, streaming execution extension, or hyper-threading, all these different things that improved the effectiveness of the CPU. And then in, what was that, 2005, the AMD produced the first 64-bit CPU. And as we will see, this changed sort of dramatically the way in which we look at memory, because of course 2 to the 64 is a lot of memory, and this is now the prevalent architecture for desktop and machines of all sorts. The 32-bit is still very present, especially now with all this Internet of Things. There are a lot of small devices that run with a 32-bit architecture because they don't need the power and the cost of 64 bits. So the CPU, regardless of the model, has a number of registers. The registers, there are 4 sort of general purpose registers called the A, B, C, and D register. You see this as, if you talk in terms of 64-bit, then it's called RAX. So this can be A, B, or C, or D. A, B, C, or D, yes. When you refer to the 32-bit version, you use the EAX, or EDX, or ECX. When you use the 16 bits, you use just the AX. And for this 4, you can also refer to the most significant 8 bits, and least significant 8 bits with AH and AL, or BL, or DL. Okay. Then there are other registers called the pointer registers, usually ESP and EBP, or RSP, RBP, are respectively the stack pointer and the stack base pointer. As we will see, manipulating these two registers are a fundamental mechanism to achieve code execution. And you can actually still refer to the least significant 8 bits, but only in 64-bit mode. So if you have a 32-bit architecture, you have only the 16 version, like BP, but you don't have the BPL. That's only available in 64-bit mode. Then you have index register, typically RSI, RDI, ESI, EDI. Usually look for source and destination index in string operations. As we will see, they also used for example, passing parameters in 64-bit mode. And similarly to the pointer register, they have the 32, 16, and 8 version, where the 8-bit version is only available in the 64-bit architecture. And then we have the instruction pointer, the EAP or RIP. Controlling the instruction pointer is the goal of the vast majority of attacks against applications, because once you can direct execution wherever you want, then you execute it to your code, and at that point you achieved a full exploit. Also important, there are the flags. So there are R flags, E flags, or flags against 64-bit, 32-bit, 16-bit. There are a bunch of flags. Important ones are like the carry flags, zero flags, sign flags, and overflow flags, because those are the ones that are used in branching. There are, a bunch of jump instructions that allow you to go in specific branch depending on this flag. So usually, for example, you have a subtraction from between two numbers, and if they're equal to 0, you can say, hey, if the last instruction set the 0 flag, so these two numbers are identical, then jump to a certain location. And then for in the case of the 64-bit, you have also these additional general purpose registers that you could use for a bunch of things, passing parameters, or anything else that you need. And then, of course, you have segments. So you have code segment, data segment, stack segment, and extra segments that you can use for whatever you want. These are 16-bit segments that usually in 32-bit protected mode are pointers to data structure that is a segment descriptor that allows you to combine the pointer with the actual offset. And in fact, in a 32-bit address space, what you have either the flat model, where you have an address and you have a linear address space. This picture is taken, as I will mention later, directly from the Intel manuals. Or you have a segmental model, where you have the segment that actually has the selector, and the selector describes a particular segment that is mapped to memory, and then the offset is actually an offset within that segment. In 64-bit architecture, fundamentally, you look at the program as a flat space. So you don't have segments. Actually, the segments are mostly ignored. Actually, there are 2 segments that could be used in 64-bit mode, but forget about that right now. Fundamentally, they are ignored, and so there is not anymore this indirection of using the segment selector. Also, even though you have 64-bit architecture, it is not necessarily the case that all the bits can actually be used to address memory. And in fact, in most CPUs right now, only 48 bits are used to address memory. So you don't need 64 bits buses that occupy silicon and all that. And in fact, an address has to be in a canonical form. That means that all the bits that are not used, so from 63 to 48, are either all ones or all zero, which means that if you think about your 64-bit space, fundamentally you have 2 to the 47 here and 2 to the 47 here. And referencing anything here in the middle would cause a fault. Yes?
Is the 48 bits, is the leftover bits just to save space and bandwidth, or is there some other use for those?
Say again?
You said only 48 bits are used out of the 64.
Yes.
So
you could use more if you want.
Also, the remaining are just present, or do they have any special purpose in this case?
That's the thing that manufacturer decided to implement.
Okay.
And fundamentally, what I think it is like 2 to the 47 is enough to do whatever you need to do. Okay, so why creating infrastructure for full 64-bit addresses when you don't need it at the moment? Of course, 10 years from now, they will be laughing at the fact that we have only 48-bit when we have a 64-bit architecture, and they had probably 128-bit architectures. And 64-bit architecture will be, devoted to your watch or something ridiculous like that.
So they're future-proofing it by having 64 bits?
Yeah, correct. In general, you want to build architectures that are fundamentally, first of all, you want powers of 2. That helps a lot in a lot of situations. And you want to future-proof your capability, but then when you actually have to be the silicon, you want to get to that perfect trade-off between being able to execute all the application you need to execute, but use as little material and components as possible because of interference, space, and all that stuff. Okay? Okay, we're gonna, let me see. One aspect, we already discussed this. Remember always the the endianness, sorry, not the signedness, the endianness in the CPUs that you will be playing with. We talk about little endian architecture. That means that if you have a number, this will actually, if you have a number that is 2 or 4 bytes or 8 bytes, in this case we have a 4 bytes number, 03, 02, 01, 00, you will see that is written from the bottom up. So 00 will be put at the lowest address and it will go up to the highest address, okay? Which might seem counterintuitive, but it's the standard for this architecture. Also, signed integers are expressed in 2's complement notation. That means that fundamentally you flip the bits, add 1 to change the sign, and ignore the overflow. So you have -1 is FFFFF, and of course if you flip the bits and add 1, you will have 1. So you see how that works. The advantage of 2's complement, as you know very well, with respect to having actually a sign bit and a number, is that you have only one representation for 0 instead of having 2, +0 and -0. Okay? Having a calculator that does actually all these conversions is super easy. I will not, tell you which to use, but it will save a lot of your time during homeworks and things like that. We're gonna take. Okay, you guys there? Everybody's almost back. All right. Okay. Let's talk briefly about the assembly language. So the assembly language is what you usually operate on. So, of course, it's a slightly higher level language than binary code, but there is fundamentally a one-to-one mapping between assembly and binary. And actually, if you get the Intel manual, it would tell, oh, this instruction is encoded as, this byte, followed by this byte, followed by this byte. And so you can see exactly how these high-level mnemonics are translated into binaries. You can also have directives. There are something that tells the assembler how to deal with certain things. You can have instructions like jumps. Note there are 2 possible syntax, and there is sometimes a holy war about what's supposed to be the correct one. For example, for me, I grew up, quote unquote, with object dump. So every time I look at source code, at assembly, I always think about, add, this to this and put it here, source and destination. Of course, Intel instead has everything opposite. So the source is here and the destination is like load, add EAX to EBX and put the result in EAX. It's just a convention. You actually can set in your debugger, your disassembly flavor of preference. It's up to you. There is, no particular reason to prefer one to the other. You can have constants, hexadecimal numbers ends with H, remember that. You can define objects by providing a label, a type, and the actual data. For example, you can say, oh, I'm going to refer to my var to this, 32-bit integer, and these are 2, one after another. This will, resolve in having these numbers actually in memory at that location. You can specify bytes, words, double words, and quad words, which is 64 bits. And for example, strings, are fundamentally lists of bytes, and you can even zero terminate them or not. These are your size, byte, word, double word, quad word, and double quad word directly from the Intel manual for your memorization. Also, remember that there is the low byte and high byte, low word and high word to reference the different parts of a single element. Memory is in the x86 is referenced using a composition of different parts. There is a base, which is sort of like the starting address, an index, which can be an offset from the base address. You have a scale, which is a constant like 1, 2, 4, 8, and a displacement and a size of the reference. So you want to know what kind of pointer, for example, you're talking about. And the address is fundamentally the base plus index multiplied by the scale and a displacement. And you can use a composition of all of them. You can have just the base, you can have only index and scale. You can have a lot of flexibility on how to specify these addresses. You can see that, for example, index and scale is often used in arrays because if you have an array of objects of a certain scale, you would use that way to address and, for example, loop on several items of that. So in this case, you can have EAX as the base address and ECX as the counter, and 4 is the size or the scale of that index plus a certain displacement. This could be, a particular reference to a value. And in this case, this would move the content of the cell at this address, so it's dereferenced into the register EDX. Of course, this could be also that we put EDX into the content of this depending on what convention you are using at that moment. For example, in this case, we from the description, you can see that we move the contents of the memory pointed by EBP minus 8. We will see that a negative reference from EBP is usually an indication that that's a local variable. Not necessarily so, but most of the time. And move it in EAX. In this case, it puts in EAX the content of the memory that EAX is currently pointing to. So this is sort of like dereferencing a pointer and putting the value here. But of course, the value could be the value already contained in EAX, which will be overwritten, of course. In this case, put EAX in the context of the memory that is the register EDX plus ECX multiplied by 2. In this case, for example, copies the value, the literal value 804A0E4 that looks like a valid address into EBX, okay? And in this case, instead, it puts in EAX the value of the memory at this address, okay? You can see this is the value, and this instead is a pointer dereference, and so that's how things are loaded. We have a bunch of instruction classes. There are a ton. Oftentimes, you will encounter some like, what is this? And you will have just to take the manual, go to it in the Intel manuals, and find out exactly what this instruction does. There are some that are very common: push, pop, move, arithmetic, multiplication, some logical stuff, and or not. Interesting are, of course, control transfers. This, as I said before, depend on the particular flag set. So the basic idea is that you have an instruction, for example, the comparison instruction, which fundamentally subtracts the two elements, but does not modify this. So it's not storing the results anywhere. They're just comparing the two and setting the flags accordingly. So for example, you can say if the 0 flag is 0, that means that the two are not equal, because of the y subtracting one from another would have returned 0 and would have set the 0 flag. So if the G and E jump if not equal, just check this flag after this instruction, and if they're not equal, we'll jump to a certain address, and so forth. Similar for other flags. Interesting. The controls transfer in binaries can be direct, means like jump to this address, okay, or could be indirect, jump to the content of this register. And for example, in static analysis, indirect jumps are typically very difficult to handle because, since they're not an actual value, when you execute the analysis on the code and you say, okay, I want to understand what are all the places that I can jump to starting from this address. If you have jump EAX, you're like, what are the possible values that EAX can take? And in certain cases, you can determine that. In certain cases, you can't. And so fundamentally, you have to assume that you can jump anywhere. And this makes analysis, of course, not very effective. You have input and output commands, and you have the magic NOP. NOP is no operation, 0x90. That means that this is a byte that you can fundamentally put anywhere, and if you jump to it, you will just go to the next byte. And if you put a bunch of NOP, it will just go through that. And this is great for padding, for example. If you're overriding an instruction, you say, you NOP it out. You just, I don't want that to happen. You do NOP, 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 NOP. Typically, imagine you have a binary that forks, receives a connection, and then forks another thing. It's really painful sometimes to debug because you have to follow the fork and so forth. So you open the binary in your favorite debugger, or favorite, actually, binary editor, hexadecimal editor, hexdump, whatever it is, hexedit, and you find the instruction where it does the actual fork, you NOP it out, and it will not fork. It will continue exactly where it is, and suddenly you can debug your binary without having to follow the fork and having all those pesky other things. And you can use it for any kind of editing. There is a call to a function that checks if your password is correct or not, and you want to get through that. You can decide to do that using a debugger, or you can decide to just NOP out the call and have a version of the binary where that call doesn't even exist, is not made. The information that I gave here is mostly taken by from these two very hefty files that describe the architecture. They're very actually interesting to read, describe the whole history, how the architecture works, and how the 64 versus 32-bit works. Of course, there are tons of details on the MMX extension, the MXX extensions, the SSE extensions, and all that stuff that are not really relevant for us. But it's interesting, and of course, you can always Google. Wikipedia is your friend. You can find a lot of information there. Now let's talk about how certain part of the system work, because understanding how these things work is relevant for our attacks. So the stack usually grows towards lower memory addresses. Okay, that means that there is another convention here where people will say, oh, I always write FFF here at the end and 000 here to say this is where memory starts and this is how it goes. To me, that's not a good way to do it. So I actually tend to represent memory with the high addresses on top. So, but it's have one mental image of what the memory is, and then go with it. It's a convention again. And so the stack grows this way towards lower memory addresses. So whenever you have to allocate another stack portion, if you're here, you allocate one here, you allocate one here, and so forth. Okay? And there is the stack pointer, ESP or RSP in 64-bit, points at the top of the stack, the last valid address. So it usually points here to this last valid address on the stack. So, the push and pop, decrements a stack and stores the value in the register, in the address contained in the register, and so forth. You know how stacks work. The important thing is the stack is used in function invocation. You know this from compiler things, but it's a good refresher. Whenever you call a function, you push a frame on the stack. Okay, that means that frame is a local environment for that particular function. So what happens is that the address of the frame, of the current frame, the frame of the caller, is stored on the stack, so you don't forget about it. Okay, and after that, your stack is, moved and sort of adjusted to actually contain the local environment for the function, including the actual parameter, the return address to jump at the end, the pointer to the previous frame, and the local variables. So this is done through the handling of these frames is very important, and is done through prologues and epilogues. So before calling a function, okay, the caller has to do some preparation, fundamentally to pass the parameters to the call function. Depending on, we will see there are different ways in which you can do calling and prologues and epilogues. We will see two versions, the one used by 32-bit architecture and the one used by 64-bit architecture. But you either set some specific register to the values, or you push values on the stack, or you do both, okay? Depending on whatever the convention. It's a convention. You can do whatever you want. Then the prologue of the called function, okay, saves the current base pointer on the stack. So it's responsible for I'm going to push, EBP on the stack so that I can restore it once I'm done. Sets the base pointer to the current stack pointer. So now the stack pointer will, just move at the, it will put the ESP into EBP and move the stack pointer down to make room for local variables. So this n value, suppose that you have two 32-bit integers, then this value will be 2 32-bit integer. This value would be 8. Thank you very much. Okay, so it will be I'm going to make 8. I'm going to go to 8 address down so that I made space for these two integers to store 8 different bytes. Notice that there is actually an enter instruction in Intel that is mostly not used. It's not used by GCC. It could be used by other compilers. The epilogue, of course, is the opposite. Usually it saves the result in EAX. Now stores the base pointer into the stack pointer, pops the value from the stack, restoring the saved base pointer, and then executes a ret instruction. And actually these two last steps are automatically done in a single instruction by the leave command, leave instruction in assembly. So this is an example. You can see there is a function there that takes as a parameter a string pointer as a local buffer of 8 characters and performs a copy. So you can see this is the top of the memory, bottom of the memory, and when there is you can see that there is the push of the parameter string and then the call to function. This is that is the C code, but this is how main or whatever function is called it func. Push the parameter on the stack, so the string pointer is going to be here, okay, and then calls the function. By calling the function, the return address is stored on the stack, and they jump to the address where the function is, and the function start being executed, okay? And once everything is finished, we will see it will just remove the parameter, so reestablish the stack to here, and everything is going to be, and the result is going to be in EAX. But let's go to see what the function does. Once the string has been pushed, the call has been made, we are right here, okay? The first thing that the function does is to save the EBP. So this is information, is the previous value of EBP, which was right here. This creates fundamentally a chain that allows anybody to go back if they have multiple function call once after another by following the EBP pointer. You can access the local environment, whoever called you before, up to the very beginning. Then push EBP moves the value of ESP into EBP. So EBP at this point will be pointing to here, and it becomes your new EBP, your new frame. So this is the frame of the new function. And then subtract 8 bytes, because it's a buffer of 8 characters. And so the stack now will pointer exactly to this last byte here. Okay? Is this super clear to everybody? EBP, ESP, everybody's super clear. Great. I talked about function calling conventions. Fundamentally, there are two things that they take care of. They take care of how you pass the parameter, and they take care of deciding who cleans the stack. Okay? So there is Linux 32-bit uses something called cdeco, and so the caller pushes the argument on the stack from right to left. Okay? EX, EDX, and ECX are caller saved. Okay? That means that the person that is called, if you care about the values of those, it will be saved by the caller. That means they assume that the callee can actually override it. The return value is in EAX, and the caller is the one that cleans up the stack afterwards. So it's the caller who decides, I'll do the cleanup. One of the disadvantages of this approach is the cleanup code needs to be replicated everywhere the function is called. So if I have a function that is called in 1,000,000 times, I will have at every location from which it's called, I'm going to have a little snippet of code that has to do the cleanup. If I put it in the caller, then I have to write that piece of code only once. Okay? But as you will see, that also has some problems. There is, this is the other approach, the standard call used by the Windows API. And so the caller pushes the arguments on the stack, and the callee cleans up the stack. Okay? One of the problems is that this does not allow for handling correctly variadic functions that are functions like printf that have a variable number of arguments. And then there is the calling convention that we will see in Linux 64-bit, where the first 6 integer arguments are parsed in register, RDI, RSI, and so forth. And except for system calls, which are specific, of course, calls, where R10 is used instead of RCX. And then additional arguments are put in the stack right to left, and the result is in RAX. So this is an example of a call. There is a function sum that you pass it in the C code. It's C equals sum 3 plus 5. So fundamentally, it pushes on the stack the 2 parameters, calls the function sum, and then cleans up the stack, okay? Because it remembers that it pushed 8 bytes here. So to restore the stack, it's the caller that has to restore the stacks and do the cleanup. So adds 8 to the stack pointer. If you remember, the stack pointer grows towards down. So adding to the stack pointer reduces the size of the stack pointer. And then moves in EAX the location where, move EAX into the location where the variable C was stored, which is a negative offset from the EBP. So that's why, since the EBP has the frame, local variables are negative offsets from that thing. So if this is your frame, right here, your local variable are here, and so if you go negative, you move down this way, and that means that these are your local variables referenced from the EBP. In the case of a 64-bit, same identical code, you can see that in this case, they move the value into 2 register and just call sum. Okay? One of the advantages is that you don't have to adjust for the stack, because in this case, you haven't used it. And then moves the return value, EAX, into, C in this case was an offset of 4 from RBP. Okay? System calls are important. In 32-bit, fundamentally, you set EAX to contain the system call you're interested in, and then you do a software interrupt. A software interrupt is an interrupt that is sent from the software itself. It's not generated by an external device, which for Linux is the interrupt 80. So if you do interrupt 80, it means I want the attention of the operating system. Operating system, EAX, is what I want you to do. Just do it, and when you return, the system call has been executed. In x86-64, you use the syscall instruction, and you use RAX to store the number. So if you look at hello world in 32 bits, suppose that you have, your string hello world, new line. 0A is a new line. Section text is your start. You have you load in EAX the number 4 that tells you which system call you're going to do. For example, a write. You put in EBX the file descriptor. The output is 1. You put the pointer to a string in ECX. You tell how long the string is, and you put this value in EDX, and then you call int 80. This will print hello world on the screen. Okay? And then you want to exit cleanly. So you put 1 in EAX. They say, hey, operating system, I'm done. I want to exit. What's your exit status? 0. You put in EBX. You call int 80 again. This is, your real hello world in assembly. Everybody's clear? Great. 64 bits is not that much difficult or different. Again, write syscall in number 1. Move in RDI the file, in RSI the reference to the string. RDX has the length. You call syscall, and then you move RAX 60 to do the exit call. You put 0 as the exit status, and you do syscall. Okay. Interestingly, there are in all this some parts that are relevant, and we will see in a second. One is the PLT and the GOT. So the procedure linking table, or PLT, is how you find out where is the function of a shared library that you want to invoke. So for example, say printf or puts, something like that. What happened is that the actual linking table fundamentally says, hey, if you want to execute, for example, a printf, you do an indirect jump in something called that is contained in the global offset table. So the actual invoking code for that through that procedure linking table, say, go to the GOT, there is the address that I linked from the remote library. Okay? Why this is done? Fundamentally because often programs don't execute a lot of the code. So suppose that I have, hundreds and hundreds and hundreds of functions that I use from all these shared libraries, OpenSSL, libc, you name it, okay? If every time I execute a program, I have to go in memory and get all these references and resolve them and put them in would be, would add a lot of overhead to starting a program. And people are impatient and they want a program to start right away. They don't want to wait for all this linking. So in many systems, this linking is done in a lazy fashion. That means the first time you call printf, printf say, oh, jump to the GOT. But in the GOT entry, there is not the address of the printf. There is actually the address of a routine of the linker. They say, oh, this is the first time that printf is called. Okay, let's find where this printf is. Okay, libc is here. Printf is inside here. Okay, let's fix the GOT. From that point on, the second time it's called, it will go directly to the GOT. Okay? And this time it will have the correct address. You're like, why are you telling us this? This is because the GOT, because it's a writable portion of the memory that contains a pointer to a function, it's a major target in exploitation. If you have to overwrite something, if you're able to overwrite the GOT, and you can write into that a specific value, the next time a printf is called, instead of calling printf, they will call your code. Okay? And as many protection, non-executable stack, randomized distribution, randomized address layout, and so forth are introduced, the GOT has be consistently, if you can override it, a source, a way to execute arbitrary code. Note that there is actually the possibility to ask the compiler to say, hey, I don't want this GOT craziness. You will have the GOT craziness. I don't want this lazy binding craziness. When you start the program, just link everything that needs to be linked and make the GOT read-only. And this is the railroad hardening option. And in that case, you will not be able to do that modification. Yes?
So if you're able to overwrite something in the GOT and you're able to write code into what it's pointing to, does that code run with root privileges or?
Will run with the privilege of the program that you're attacking.
Okay.
And we will see in a second what that means.
Right. Thanks.
A similar story is with a detour section. Remember that it was this init and there is code that is executed before your code is actually executed and after you do exit. And fundamentally, there is this detour section that contains code that can be put there to be, for example, perform operating system related cleanups and things like that. The detour section where you can operate sometimes, again, depending on which particular set of compilation flags you have used, might be not read-only, might be writable. And the section is a list of 4-byte addresses where you will jump to each of those after having exited. So if you're able to modify the detour section and put a pointer to your code, that's another area of your binary where you can perform an override. And that's why understanding the ELF format, what are the section, what are the privilege, is the GOT. I tell you, yesterday I was looking up the GOT, and now with Games of Thrones, GOT is not a good term to search on the internet. I didn't realize that until it was, I had to actually do it. And so, running this modifying this is a good way to trigger code execution. And we will see what that means. But, so let's talk about we talked about how the code is put together, how it works. When the code is loaded, when you invoke a program, the operating system takes the ELF image and decide how to load into memory. So we'll take all this information about the ELF and decide, oh, this segment goes here, this other part goes here. We'll create a process image for that particular file. If you're interested, in Linux, if the proc file system is actually enabled, looking at the maps shows exactly how is the layout in memory. And this can be very useful sometimes to debug, just to debug and understand what's going on. Then if there are relocation things that need to be modified are modified, and then the instruction pointer is set to the starting address, okay? Which is, if you remember, one of the fields in the header of the ELF format. And at that point, execution begins. And in fact, for example, if you don't have the ELF format, we sometimes have to operate with what we call the blob, a binary large object. And in this case, you have a bunch of instructions. And finding out where should I start? It's actually a difficult problem because the executor of that blob knew, because they built the blob, but when it's given to you, for example, is a piece of firmware that runs on some obscure architecture. This is something that we were discussing Friday in my lab. It's very challenging to find out what is the entry point. Where do you start from? So ELF gives you that because, of course, it's part of the format itself. So when something is loaded, in a 32-bit, you will have sort of the high memory is used for the kernel, and the lower part, the lower 3 GB, are reserved for program addresses, while in 64-bit, you have fundamentally a 128 terabyte program and the high part of the kernel that is mapped on top. And exactly, you have this, crossover where you have either all set to 1 or all set to 0. Yes?
Why is the kernel smaller on the 64-bit?
I think that it's only, that's a good question, and I don't have a good answer for that. I will have to look it up. That's a good question. I don't know. Could be also wrong. The process structure, if you look at a process, no, my slide could be wrong. Could be that it's 512 gigabytes, and this might, I don't remember. You have this, bottom of memory to top of memory. Initially, you have the environment with strings and pointers, okay? Then you have argc. Remember, argc is the parameter that you pass to main. And after that, you actually have the stack that is allocated and grows in this direction. In the middle are the mapping of the shared library. Then you have the heap. The heap goes in grows in the other direction, so towards higher memory addresses. And then you have your BSS, and so uninitialized and initialized data segment, and then you have the actual code. Yes?
What is your bottom of memory on bit set?
Is why it's at 808? Because I think that's where they usually map the beginning of the code text. In 32 bits, I think that's correct. Is it incorrect? Well, I will check it, but I think that there is actually something. First of all, there is for sure a hardening that prevents you to map 0 because of null pointer dereferences. And usually the text code, I think it's mapped starting from this address, but I'll check it. It's shifted by 4?
The 0 goes on the right side. That's fine.
That's definitely 3, 4, 8. I'll check, definitely. I think you're right. I think there is a 0 too much on the left. So, and this goes now to the point of what is the code, on what privilege you execute the code when you do an attack. So to do that, you have to understand that there is fundamentally 2, but actually 3 UIDs and group IDs. Every process has a user ID and a group ID that determine what the process can and cannot do. So the real UID, the effective UID, and the saved UID. So the real UID is associated with the user who actually owns the process. Okay? So if you run any program, the real UID will always be you, whatever account you're logged in at that time. The effective UID is the ID that is used in understanding what you can and cannot do. Okay? And the saved UID, as we will see, is used just to temporarily store a UID so that you can change your privilege and go back to it. So the cool feature, or the important feature, is that a program that has this set UID bit set to 1 means that when you execute this program, you will keep your real UID, but you will get the effective UID of the owner. Okay? So you see this little S here means that this binary is set UID. This is how you escalate your privileges in Unix. You get a set UID program, and by running your code in that context, it will run with the effective UID of root. So finding something set UID root is, those are the binary that you want to launch. Because if this bit is not there, that means that exploiting that file will not give you anything. It will be still executing code as you. So escalation has 2 routes. Either you break the kernel, and you are able to execute your code in kernel context. In that case, you're acting as the kernel. Or you have a binary that is set UID that will be able to give you the privilege. And in fact, your homework 3 will be a whole series of binaries at different set UID that will always set UID to the next level. And so you will have to break, 10 or 11 binaries in order to get to the end of the homework. And everyone will give you access to the next one and so forth. But usually it's not so contrived, but in this case, you have root. And of course you have root because here, for example, this command is the passwd command. As you all know, this allows you to change your password. Okay? If you do passwd on Unix, you can change your password. That means that you are modifying the ATC shadow file in the file system that is owned by root and is not word readable even. And so you cannot be modified by anybody. Otherwise, anybody could change the root password and log as root. So you need to create a program whose only task is to do that. It's not a shell that allows you to do anything. It's a very well-defined task that this thing allows you to do, and only that. But if you can convince the magic program to do a lot more than just changing the password, either because of confused deputy situation, you can convince the file to, for example, change the password of a different user, or because is deployed in the wrong way, you are able to, for example, change other files with as root. But most of the time, you would provide some kind of memory corruption vulnerability that will smash the stack, modify the heap, change the state of the program, and lead the program to do things that it should not do otherwise. So it's important to understand the setUID behavior. So when you run setUID, you fundamentally set all the UIDs to the specified UID. So the first call, if you're root, for example, and you do set UID, I don't know, suppose that my user ID is 50. If I'm a root program and I do set UID 50, I drop completely my privilege, and now I am 50. Okay? So for example, a lot of security programs, for example, they have to bind a socket, that requires root privilege. What they do, they create the socket, and then they drop the privilege. They call setUID, and they become, user nobody, something like that. Okay? And by doing that, they did all the things that they have to do that require privilege, and then they decided, so if somebody sends code to me, at least they will not run code as root. They will run code as user nobody that usually has little access to resources. It's still bad. Dropping privilege is not, saving anything. Having somebody being able to execute code with any privilege on your protected machine is a bad thing. But at least it's not running as root. Then you can set your effective UID, okay? And in this case, of course, you can do it if you do root, if you're root. But otherwise, if you set this UID, the UID must be the real UID, and you cannot set the effective UID to whatever you want. Otherwise, of course, you would become whatever you need to become. And then there is set res UID, which allows you to set independently the real, the effective, and the saved UID. And this is useful sometimes because especially if you are a root process and you want to switch to an effective UID, for example, because I have to do some operation on behalf of user Giovanni. So I become user 50. I do this operation so my effective UID reflects what I can do and not what root can do. And then having saved my UID, I can switch it back because my real UID is 0, is root, so I can do this switcheroo. So I can temporarily have the effective UID of another user and then switch back to the root ID. Yes?
What's stopping everyone from switching to ID 0?
Because you can't. You need to call these functions, you have to write the right privilege. If you don't have UID 0, you cannot say, oh, I'm setting the UID to another user. It stops, the operating system stops. When you call that, well, the function like, who are you, to setting effective UID 0.
If I go from 0 to 50 or something, how do I get back to 0?
By saving your 0 to the saved UID, which allows you to restore your saved UID the way you want it.
But couldn't anybody set that saved UID?
No, because your real UID cannot change. Your real UID is who you are. And real UID 0 can switch around their effective UID. And in fact, if UID 0 does a set UID and changes also its own real UID, then it cannot go back. Set UID is a drop without return. And instead, with res UID, you can actually change your privilege forward and backwards. OK. We have a few minutes. Just I want to talk about a few tools that you will have to, some of which you will familiarize yourself with. An important part of what we were going to do here, I will give you binaries. So programs that you have to break, fundamentally. And in order to do that, the first step is disassembling. So it's taking the binary, the raw ELF, and extracting assembly so that you can analyze it and understanding. Disassembler typically can be linear, so they go through it and they translate every instruction as they found it. Object dump is an example of a linear disassembler. And can be recursive. That means that they actually identify function and they jump to the functions. So they're not confused if they're less prone to be confused by a file that is not in the right format, that has the sort of like, for example, unparsable instruction in the middle. Even though one interesting property of x86 per se is that self-realigns pretty fast. Even if you start disassembling from any point, very soon you will start disassembling the correct flow of execution. An interesting tool that I strongly suggest is Radar. We will have a mini tutorial about Radar later in the class. Supports reversing and vulnerability analysis, so it is not just a pure disassembler. It actually provides some analysis, helps you find specific constructs within the binary. Supports scripting, and more than anything, it's free and actively developed. I started using recently because mostly I've used IDA Pro in the past, but I found it really useful, even though the learning curve is a little steep. It is actually a tool that can be used in many situations and also as a debugger, so it's very useful. The king of the disassembly is IDA Pro. The unfortunate aspect of IDA Pro for this class is that it's very expensive, and so if you're a professional, it is definitely worth the $1,000, $2,000, $3,000 of investment, depending on what version you have. One thing that is interesting is supports disassembly, but also decompilation. So you have a binary, you press a button, F5, and you get the source code, which in understanding what's going on with a binary is awesome, okay? And they're very good at it. So you will not be allowed to do that. So if you have an IDA Pro license, please do not, in your assignment, use the F5 key, okay? That is not using the compilation. I want you guys to really think and learn about the details of how assembly works. I think the decompilation is super useful when you have a very large binary. When we participate in capture the flag competition, nobody is really, going through the binary step by step. Or this not most of the time. Most of the time, you try to get decompiled code. And in fact, small digression. This last capture the flag at DEF CON that happened in August 2017, in order to make this whole decompilation impossible, they decided to come out with a complete new architecture. So they came out with something called clemency, which is a 9-bit architecture where every byte is 9 bits. And the endianness was middle endian. That means that every address was 27 bits, and it was in 1, 2, 3 order. And by doing that, nobody had the tools. We were super lucky because actually the person, Chris Eagle, who wrote the book about IDAPRO, was playing with Shellfish with our team. Usually he plays with a different team, but this time was playing with us. And in few hours, we had the ability at least to see the actual assembly in IDAPRO. Looks like somebody was even able to, some magic transformation, have a decompiler for clemency. We saw some screenshots, but at this point. But at that point, suppose you show up, you get a new architecture, you don't know anything about it. So the first few hours of that competition, we did exactly what we did today. Okay, what are the instructions? What are the bit formats? How do you do addressing? And and this thing has even a bit in the CPU that would describe if the stack is going up or down at a certain point, and you can change that bit dynamically. So you can do all sorts of different things. Yes?
Is IDAPRO available in Cecil?
Absolutely not. IDAPRO, for this class, you are not allowed to use IDAPRO. I want you to use open source software. Radare, I think it's a great example. You don't need that. You can use object dump and GDB. That's really, GDB is really everything you need. Of course, we will see Pwn tools, Radare, Anger. All these other tools can help considerably do your job, and we will see all these tools, and we'll talk Wednesday about that stuff.